Hello everybody, and welcome to exercise 3 on page 32 of the workbook. And in this exercise we're going to be talking about finding the area of a region in two separate ways and kind of comparing the methods. Okay, so let's read this together. So they'd like us to consider the region bounded by the curves y equals x squared minus 1, 4x minus y equals 1, and y equals 3, shown to the right. We'd like to set up integrals that represent the area of the region in two different ways, one in the dy direction and then one in the dx direction. Okay, and then we get to choose which way of setting up the integral might be the easiest to evaluate. Okay, so why don't we start by labeling the curves, okay, just so we can see which is where. So y equals x squared minus 1, that's a parabola, so that must go with the curved portion of our graph here. Okay, and I'm going to try to do this in such a way that we've got space later on. Okay, and then 4x minus y equals 1, that's the equation of a line. Okay, and you think about it, that must go with this line that's sort of slanted here. Okay, and then finally y equals 3, that's a horizontal line that's sort of sitting up here in our picture. Okay, so those three curves kind of form the boundaries of this region that we're looking at. Okay, so let's start with part A here. Integration in the dy direction. Okay, well, if we've got a dy in our integral, then that means that dy is like the height of our rectangle, so what we're really talking about is the right minus left way of thinking about area between a curve. And that means that we need to solve for x in terms of y to be consistent with the method that we developed. So if you look at our curves one at a time here, let's see, if we start with y equals x squared minus 1, what would that look like if we solved it for x? Okay, let's do a little algebra here. So we can add 1 to both sides and then solve for x. And we're going to get x equals the positive square root of y plus 1. We can actually ignore the negative square root because in our picture x is positive everywhere. Okay, so if we label that in our picture, that's came from the parabola, and so just a second way of writing that equation is what we just came up with, x equals the square root of y plus 1. Okay, and then we come to 4x minus y equals 1, what would that look like if we solved it for x? Well, let's see. So we will add y to both sides and solve for x. We're going to just divide both sides by 4 and get 1/4 times y plus 1. Okay, and that's just a second way of writing the curve over here on the left, 1/4 y plus 1. Okay, and then finally y equals 3. There are no x's in that equation, so it's not even possible to solve that for x. Okay, and it turns out that's not even going to play a role in this solution because, take a look at the picture here. If you draw a typical rectangle that goes from the left-hand curve to the right-hand curve, notice that for this region, the curve that's on the left is always this line, and the curve that's on the right is always this parabola. So the only two formulas we're going to need are these two. Those are our left and our right curves. Okay, so that means that when we set up the area in the dy direction, we're just going to integrate the y plus 1 that's on the right minus the 1/4 y plus 1 that's on the left. Okay, what would the limits of integration be here? Okay, well, we're integrating with respect to y, so our limits should be y values. If you look at the picture, the y value at the bottom of our region is minus 1, and the y value at the top of our region is 3, so those should be our limits. Okay, and so that's the answer to part A. That would be an integral that would give the area that we're talking about. Okay, what about part B? Okay, well, part B would like us to integrate in the dx direction, which means that we just need to turn everything around. Okay, and so that our picture doesn't get too cluttered here, I'd like to redraw the curve, okay, just so that we can kind of mark it up and label it again. So here's my best attempt at drawing that area that we've got. Okay, and so we'll do what we did before and just go back. Let's erase a little clutter and visit these curves one at a time. So starting with y equals x squared minus 1. Okay, if we solve that for y, well, it already is solved for y, so we don't need to do anything there. Okay, and then we come to the second one, 4x minus y equals 1. Okay, if you take that and solve it for y, you're going to get y equals 4x minus 1. Okay. And then the third curve, y equals 3, that's already solved for y. Okay, so we've got 3 involved curves. Let's go over to the second picture that we drew and just labeled them. Okay, so we've got the parabola here. Okay, we've got the line, y equals 4x minus 1, and we've got the horizontal line, y equals 3. Okay, now how would we set up an integral in this case? Well, integrating in the dx direction, we want to think top curve minus bottom curve. Okay, and so from the picture, I can kind of see what the bottom curve is of this region. It's going to be the parabola that I'm highlighting here. What is the top curve of the region? Okay, well here we run into a bit of a snag because notice that there are 2 curves on the top of our region. There's this line for the left-hand part, and there's this other line for the right-hand part. We've got 2 tops to our region. Okay, so what that forces us to do, if we want to integrate in the dx direction, is to split this into 2 pieces. Okay, we need to do one area that represents the left-hand side of the region, and then a second integral that represents the right-hand part of the region. Okay, so let's see if we can write down those integrals one at a time, starting with the area that I just shaded to the left. Okay, so that's going to be the integral of the top curve, which would be the 4x minus 1, minus the bottom curve, which would be x squared minus 1. What would the limits for that first integral be? Okay, well, we're going to start here, and if we sneak a peek back at our bigger picture, x equals 0 was the point over here at the left. And this dotted line, if you look at the picture, that's sitting right here. That's x equals 1. So we're going to be integrating from 0 to 1 to get that area. And then what about the second area? From here to here. Well, same idea, just that our top curve has changed. So now our top curve is 3, and we're going to subtract x squared minus 1. And what would the limits of integration for that integral be? Well, this time we're going to start at 1, and we're going to stop when we're over here at this point to the right. And the point at the very right, we can see from the picture up above, is 2. So we should be integrating from 1 to 2. Okay. So we have done A and B. We have described 2 different ways of finding this area. And now the question is, if you had to actually calculate the area, which way do you think would be easier? Which way would be better here? Okay, would you prefer to do this integral, or would you prefer to do these 2 integrals? Okay, well here, I think there's a little bit of room for interpretation. Okay, you may very well have different opinions on this. I think there are advantages to both ways of thinking about it. So up here, this might be advantageous because there's just one integral to calculate. There's not 2, there's just 1. But on the other hand, that one integral involves a square root, okay, and a fraction. Down here, we do have to calculate 2 integrals, but the advantage is that the things in the integrals look a little bit easier to calculate. Okay, so it's kind of up to you which way you think might be the easier way to go here. Okay, I'm going to just pick one of them and choose the integral that we did in part A. Okay, just because there's one integral there, and see if we can do that to find our area. So using our solution to A, area is, okay, I'm just going to recopy that integral. And remember that the square root of y plus 1 is y plus 1 to the 1/2. Okay, and I'm going to go ahead and just do some algebra and take this minus 1/4 and distribute it through. I'm looking up here now. So minus 1/4 y minus 1/4. Okay, if we just go ahead and get antiderivatives for those three things, technically we would need a substitution for the y plus 1. I'm just going to write down the antiderivative and ask you to think about it and check it. We'll get 2/3 y plus 1 to the 3/2. Essentially, we're just using the power rule there. Okay, and then integrate 1/4 y. The y is going to, antiderivative is going to turn into y squared over 2, so we're going to get y squared over 8 for that term. Okay, and then antiderivative of 1/4 is just going to be y over 4. Okay, we'll evaluate between our limits, 3 and -1. Okay, and the rest is really just substituting in our values and seeing what we get here. All right, so let's see, upper limit, plug in 3's for all of those y's. Okay, and then lower limit, plug in 1's for all of those y's. Okay, -1 into the first term. One nice thing that happens is we get a 0 for that. Okay, minus 1/8 plus 1/4. Okay, and from here, it's really just a matter of either going to your calculator, or if you like, you can work this out to an exact number. Okay, and after just doing some arithmetic here, you're going to come up with a final answer of 10/3. Okay, so that should be our area. Okay, and if you have a little extra time, you might just confirm that if we had chosen the second way of doing this, of adding those two integrals up, we should get the same answer, 10/3, for this problem.